And so we're going to start off talking about precipitation reactions. This is one subgroup of a broader class of chemical reactions called double displacement metathesis reactions. They mean the same thing. So whether you use metathesis or double displacement, it's the same reaction, just two different names to describe the same type of reaction. And so precipitation reaction is a subgroup of double displacement. So if I was to write like a flow chart, if I had double displacement, there are two types of double displacement reactions. One is precipitation, the other is acid-base. And they both do the same thing, the same process in writing the products. It's just that one involves acids and bases. The other one involves producing a precipitate. And so these are the two types of double displacement reactions. And the other broad group that we'll talk about later are redox reactions. And redox reactions are separate from double displacement. So there's no overlapping between double displacement and redox. If something is double displacement reaction, it cannot be a redox reaction. And so for precipitation reactions, which is a subset of double displacement reactions, what we need is we need two soluble ionic compounds to react to form at least one insoluble solid. So you start with two soluble reactants, and the way you know the reactants are soluble is that they have this subscript AQ next to it. So if you see a reactant with AQ next to it, it is soluble. So you want to look to make sure both your reactants have AQ. And then we're going to form at least one insoluble solid, and that one should have a subscript S. And that's the requirements for precipitation reactions. Both reactants have to be soluble, and you have to form at least one precipitate. And so the general form of a double displacement reaction, if we have the general compound AB plus CD, now A and B represent cation and anion, and C and D represent a cation and anion. All we're doing in double displacement reactions is we're taking the two cations and switching them. So now we get two new products. And at least one of the products is a solid. And so the way you know which one is solid and which one is aqueous is based on solubility rules that we'll touch on in just a bit. So based on the solubility rules, you know whether or not the products will be soluble or not. And so it's very important you learn the solubility rules because it helps you predict precipitation reactions. So this is the general form that we use. All again is we're taking the two cations, we're switching them, we're forming two new compounds. So for example, we take silver nitrate and sodium chloride. We take the silver and the sodium ions and we switch them, we get silver chloride and sodium nitrate. The way we know that silver chloride is a solid is based on the solubility rules for ionic compounds. Now, just to let you know, I'll give you some hints along the lecture, but all nitrates are soluble. So anytime you see a nitrate compound, it's always going to be soluble. That's tip number one. So whenever you're writing these equations, if you see a nitrate compound that's an NO3 as an anion, they're always going to be soluble. That's always soluble. The other hint or tip I can give you, not a hint, a tip, is that all group 1 cations form soluble compounds. So if you see a group 1 cation in a compound, it's going to be soluble. So that's like lithium, sodium, potassium, cesium, rubidium, etc. Those are two tips to remember. One is, the first tip is all nitrates are soluble regardless of the cation. You're just looking for NO3. If you see NO3, automatically you know it's soluble. The other tip is that all compounds with a group 1 cation are soluble. And so that's why sodium nitrate is a soluble salt, and that's why silver nitrate is soluble, because it contains the nitrate anion. Sodium chloride is soluble because it contains the sodium cation. And silver chloride, we'll look at the rules in just a little bit, but silver chloride is insoluble. And so if you were to do this experiment, when you mix sodium chloride into silver nitrate, you form a solid precipitate, which is silver chloride. And so that's the insoluble salt that precipitates out. And so this is what we're doing when we're writing precipitation reactions, is that when we mix these two reactants together, at least one product comes out of solution. So now let's take a look at the solubility rules. Now there's an extensive chart in table 4.1. I'm not exactly sure if it's still on page 143 or not, but if you take a look, table 4.1 in your chapter 4 gives you an extensive list of soluble and insoluble salts. And I strongly recommend that you make flashcards. On one side you can have the anion, for example, and on the other side you can say what is soluble or what is not soluble. So for example, for halides, and halides are your group 17 anions. So for things like chloride, bromide, and iodide, these are referred to as halides, all soluble except I believe it's copper 1, lead 2 plus, silver plus, and mercury 1. So all cations except these 4 that I've listed form soluble halides. So if you look at a compound, you see it has one of these 3 anions, and it has a cation that's different from the 4 I put up here, it's going to be a soluble compound. So that's a very important rule to remember. So again, halides are your group 17 anions. So to give you some highlights from that chart, and that was one of them, the halides. Another thing that's a highlight is, as I said earlier, all group 1 and ammonium salts are soluble. So again, if you see a group 1 cation or ammonium in a compound, it's a soluble salt, regardless of the anion. You just look at it as lithium, sodium, potassium, rubidium, cesium, or francium. It's group 1, it's soluble, or ammonium. Those are the 2 conditions. We talked about halides. Now sulfates. Sulfates are all soluble except these 5 listed here. So calcium, strontium, barium, silver, and lead 2 plus. That pound sign is just extra, didn't need it. That's another important rule. As I said earlier, all nitrates are soluble. Another important solubility rules about hydroxides. Again, hydroxides is OH minus. And so all hydroxides are insoluble. Notice here the difference. All hydroxides are insoluble, except those of group 1 ammonium and heavier group 2 cations starting with calcium. So all other types of hydroxides, if it's not one of these cations, is insoluble. Now for the other types of anions, such as carbonate, phosphate, chromate, things like this, usually all insoluble except for group 1 or ammonia. These are kind of the highlights of that solubility chart. So I'll take a So here we have some combinations of soluble ionic compounds. We want to write the net ionic equation of the following reactions. So these are all going to be precipitation reactions. We want to know what the net ionic equation is. And again, the net ionic equation only shows the reacting species. So what I'm going to do first is I'm going to write the regular equation called the molecular equation. And then I'm going to write the ionic equation and then the net ionic equation. So the first thing we have to do, since this is a double displacement reaction, is we have to switch the two cations and form two new products. So what I like to do first is let's break apart each compound into their cation and anion. And again, CaCl2 is the anion chloride. Some students write Cl2 minus, which is not correct. It should just be Cl minus. And then with sodium carbonate, we have Na plus and CO3 2 minus. And so once we have them separated, we do a crisscross where we combine the opposite cation with the other anion to get two new products. So when we do this reaction, our two products will be sodium chloride and calcium carbonate. And now we can go ahead and ask ourselves, is sodium chloride soluble or insoluble? And the answer is, since it has a group 1 cation, it's soluble. Calcium carbonate, we ask ourselves, is this soluble or insoluble? And all carbonates, except group 1 and ammonium, are insoluble. So this would be the salt. So now what we can do is we can write the molecular equation. And here it's important that you put the subscripts of the physical states. So you do need to balance it before you continue writing the net ionic equation. So to balance it, we got to put a 2 right here. And this 2 gets distributed to the sodium and to the chloride. So again, this first equation is called a molecular equation. Now what we need to do next is everything that's aqueous, we need to break apart into ions correctly. So notice that calcium chloride, sodium carbonate, sodium chloride are all AQs, so we're going to break them apart into their ions. And you have to break apart Humpty Dumpty correctly so we can put them back together. And notice that calcium carbonate is a solid, so we're not going to touch that because it has a solid. If it's a solid, liquid, or gas, we do not touch it. So now we're going to break apart the aqueous compounds into their ions. So we get, and again, a common mistake is students will put Cl2 minus, and it should be 2Cl minus. That's all the reactants written as ions. And we do the same thing for the products. but we just do it for sodium chloride. And this is called the total ionic equation. So everything that's aqueous, we write as ions. Let me just move this calcium carbonate. Okay. So now we, great stuff. Let me just write it. There we go. So now we have all the aqueous written as ions. What you want to look for is which ions are exact, or which species are exactly the same on both sides of the chemical equation. We got a plus sign there. So you'll see here 2 sodium ions on the reactant side, 2 sodium ions on the product side. So we can cancel those out because they're exactly the same. 2 chloride ions on the reactant side, 2 chloride ions on the product side. We can cancel these out. They're exactly the same. And so these ions that we crossed out are called spectator ions. And so the spectator ions are the ions that are not involved in the reaction. So here, the spectator ions are sodium ions and chloride. And usually if you have a product, typically when you have a product that's a group 1 compound, it's always going to be your spectator, always going to contain your spectator ions. And then what we have left is the net ionic equation, which would be so these are the reacting species in this reaction. So only the calcium and the carbonate react to form calcium carbonate. So again, the first equation was the molecular equation. And the second equation, we took everything that was aqueous and we broke it apart. If it's a solid, liquid, or gas, we keep it together. And then what we have left, we mark out these spectator ions. What we have left is calcium plus carbonate ions gives us calcium carbonate. So we'll look at another one. Next we have iron 3 nitrate and potassium phosphate. And by the way, I'm doing it a step by step, but sometimes you could probably look at these and write the net ionic equation just by seeing it. That's fine. I just like to show all the steps for those who may not see that. So the first thing we want to do is break apart these 2 compounds. So we have iron 3 nitrate. So the iron 3 plus and nitrate ion, and then we have potassium and phosphate. So since this is double displacement, we're just going to switch the 2 cations. And we're going to get 2 new products. So we get potassium nitrate and lead 3 phosphate. And here notice that potassium nitrate is a group 1 salt, so that's going to be most likely our spectator ions will come from this compound. So now we need to write the molecular equation. So we take our reactants. Now, when we're writing our products, we have to look at solubility rules. So potassium nitrate is a group 1 salt, so it's soluble. It's going to be aqueous. And iron 3 phosphate. So for phosphates, only group 1 and ammonium cations form soluble phosphates. So this would be insoluble. And so this is the molecular equation. We need to balance it before we can continue. So to balance it, we just put a 3 here. When you're balancing double displacement reactions, it's best to balance it based on the type of ions. So you see here we have 1 phosphate and 1 phosphate. So the phosphates are balanced. We have 1 iron is balanced. But as you see here, we have 3 nitrates and 3 potassiums. So that's why we need to put a 3 in front of potassium nitrate. So when you're balancing double displacement reactions, it's always best to kind of balance it based on the type of anion or cation. Don't break those apart. It makes it a little bit more complex. So now everything that's aqueous, we're going to split apart. Remember that 3 after the nitrate comes in front. Now that 3 in front of KNO3 gets distributed to the potassium ion and the nitrate. And then the iron 3 phosphate we leave intact. And so now we look to see what is similar or the same on both sides of the equation. We see 3 nitrate and 3 nitrate, so we can mark those off. So nitrate is a spectator ion. We see 3 potassium ions and 3 potassium ions. That's a spectator ion. We can cross it out. And what we have left is the net ionic equation. So again, the first equation is called the molecular equation. All the reactants and products are written in the neutral form. Second equation is the total ionic equation, where we break apart the aqueous compounds into their ions. And the third equation is the net ionic equation, where we remove the spectator ions. So in the third example here, we have barium hydroxide and aluminum sulfate. So we want to write the precipitation reaction of these two compounds. And so the first thing is we need to break them apart. And so here we're going to switch the 2 cations to form 2 new products. And so we get aluminum hydroxide and barium sulfate. So now we need to ask the question, are these soluble or insoluble? And for aluminum hydroxide, only the group 1 and ammonium, or excuse me, the group 1 ammonium and heavier group 2 cations starting with calcium are soluble. So aluminum hydroxide would be insoluble. Next, we have barium sulfates. So for sulfates, the insoluble sulfates are calcium, strontium, silver, and lead 2+, and barium. So barium sulfate is an insoluble salt. And again, the way I know these is by referring back to the solubility rules. So now we write our molecular equation. And notice here in this example, you had 2 precipitates. So it is possible to have 2 precipitates. Now we need to balance it. So we need 2 aluminum. So let's put a 2 here. If we do the 2 aluminum, then we need 3 hydroxide. So we'll put a 3 here. Now we need 3 barium. We put a 3 here. So this is the balanced equation. Now everything that's aqueous will go into break apart. Now remember that 3 goes to the hydroxide as well, so we have 6 OH minus. And now we do the products, but notice that both products are solids, so we keep them intact. And now in this example, notice that we can't go any further because both the products are solids, so the ionic equation is the net ionic equation. So this would be the net ionic equation for a reaction involving barium hydroxide and aluminum sulfate. So since both products are solids, there's no spectator ions involved in this reaction. Now we go to the fourth example. We have zinc nitrate and copper 3 chloride, excuse me, cobalt 3 chloride. So we want to break this apart. Then we're going to switch to cations to get 2 new products. Now notice when I write the formulas, they're written correctly. So now we have to ask ourselves the question, is zinc chloride soluble or insoluble? If you refer back to a few slides, you see that all chlorides are soluble except copper 1, silver, lead 2, and mercury 1. So zinc chloride is aqueous. Cobalt-3 nitrate, is it soluble or insoluble? Since it has a nitrate, as we said earlier, all nitrates are soluble. So since both of these are aqueous, there would be no reaction. If no precipitate is made, no reaction occurs. It's just going to sit there in solution. So we can have some reactions that give one precipitate. We can have reactions that give two precipitates. And if it doesn't give any precipitate, it's no reaction. Now we get to the last example. We have lead nitrate and copper to bromide. So again, we're going to break apart two compounds. And we're going to switch the cations to form two new products. And we get copper nitrate and lead to bromide. So now we have to ask the question, are these soluble or not? So copper to nitrate, since it's a nitrate, it's soluble. Lead to bromide, based on our solubility rules, we know this is that's right, a precipitate. So that's a solid. So now we can write the molecular equation. And this is the molecular equation. Everything that's aqueous, we're going to break apart. Oh no, I forgot to balance it. Not that. Oh, it's already balanced. That's good. Now lead to bromide, we don't break apart because it's a solid. Now we look for what's identical on both sides of the reaction. So you see here, two nitrates. So nitrate is a spectator ion. Copper 2 plus, copper 2 plus. Copper 2 plus is a spectator ion, so what we have left is the net ionic equation. So again, when you react lead 2 nitrate and copper 2 bromide, the only things that react are lead 2 plus and bromide. So the first equation is the molecular equation. The second equation is the total ionic equation. And the third equation is the net ionic equation. Again, the key thing is to know your solubility rules so you know which product or products will be soluble or insoluble. We're not to molarity yet. We're to the second type of the double displacement reactions. Remember, the first type was precipitation reactions. The second type of double displacement reactions are acid-base reaction. So if obvious, the first question is, what is an acid? And so there are different theories about what an acid is. We'll cover two fundamental theories. If you take General Chemistry 2, you'll learn more in depth about the acid behaviors and base. So first off, the way you identify an acid is typically the first element in the formula is an H. Obviously, water is not, water in General Chemistry 1 terms does not classify as an acid. So that's like an exception to this rule. But anytime you see a hydrogen listed as the first element in the formula, at least in General Chemistry 1, that's a good indication that it is an acid. And so the simplest theory of an acid is Arrhenius theory. And it simply says that when you put a compound in water, if it produces H+, when it produces H+, in solution, it's called an acid. So for example, we take hydrogen chloride gas, bubble it through water, we form H+ and Cl-. So HCl in solution is a acid. If we take HNO3 in water, we form H+ and NO3-. So these are all examples of acids. And again, we form H+ in solution. Now there are different ways you can write these reactions. Notice here that I put H2O on the arrow, and we have H+ and Cl-. Another way you can write this reaction is like this. And if you write H2O as a reactant, it would be written like this. So the reason I wanted to show you this is that H3O+ and H+ are basically the same thing. It's just that if you include water as a reactant, it becomes H3O+ because the hydrogen moves to the water. If you just put HCl, then it's just H+. But either H+, H3O+, and H3O+ is called the hydronium ion. If you form this in water, it's an acid. And as we mentioned in an earlier lecture, strong acids are strong electrolytes, and these are the common 6 strong acids. So it's very important you know the common 6 strong acids, because all other acids would be weak acids. So again, strong acids are strong electrolytes. So it's very important that you know which ones are the common strong acids. Now you see for strong acids, the arrow only points in one direction, which is a characteristic of strong electrolytes. But for weak acids, and there are lots of weak acids are weak electrolytes, and they have this double-headed arrow indicating that both sides of the reaction are present. You have molecules and you have ions. And again, when you put HF in water, you form the H3O+ ion. So it's still classified as an acid. So again, acids, for most purposes intended, H is the first element in the formula. When you put it in water, it forms H+, or you could say H3O+. There are 6 common strong acids. Weak acids have a double-headed arrow, which signifies that reactants and products are present at the same time. Now for bases, now these are going to be your soluble hydroxide compounds. If you remember when we talked about solubility rules, we mentioned a few of them, and one of them was hydroxides, and we said that soluble hydroxides are group 1 ammonium and heavier group 2 hydroxides. And so for strong hydroxides, strong bases, we're looking at the group 1 and heavier group 2 hydroxides. And so the simple theory about Arrhenius, or about a base, is the Arrhenius theory, which says when you put a substance in water, it produces hydroxide ions. So for example, you take sodium hydroxide and you dissolve it in water, you get sodium ions and hydroxide. So according to Arrhenius theory, it's a base. If you take strontium hydroxide, put it in water, you get strontium ions and hydroxide ions. And therefore, according to Arrhenius theory, it's a base. And again, strong bases are strong electrolytes. Now, another type of strong base besides hydroxides are oxides. So when you have an oxide like potassium oxide, you put it in water, it forms hydroxides. So the oxides and their corresponding hydroxides are all strong bases. So again, to repeat, when you put oxides in water, they form hydroxides. So they'll be considered a base as well. Now with weak bases, these are generally going to be compounds that contain a lot of carbon and hydrogen, and they have a nitrogen atom present. These are what we call a group of compounds with that type of formula are called amines. And so you may have heard of a common amine called caffeine. Caffeine is a weak base. What else? Nicotine is found in tobacco or in vaping. Nicotine is a weak base. Amphetamine, which is found in some drugs, amphetamine is a weak base. So these compounds that contain nitrogen, which are commonly called amines, are weak bases. So again, an amine is a compound that contains a lot of carbon and hydrogen, and it has at least one nitrogen. So for example, this would be an example of a weak base. So it has a bunch of carbon and hydrogen, and it has an NH2 at the end. And so when you put weak bases in water, again, since it's weak, we see the double-headed arrow, which is a characteristic of weak electrolytes, and we form the ammonium cation and hydroxide. So since we form hydroxide, it's a base according to the Arrhenius theory. But again, the double-headed arrow represents or signifies that both reactants and products are present at the same time. Whereas the single-headed arrow only indicates that there's only products at the end of the reaction. Whereas double-headed arrow indicates that both sides are present. So we have acids and we have bases. And again, if you like acids and bases, when you go to Gen Chem 2, they go more in depth into how acids and bases behave. And so we're only going to talk about the reaction involving strong acids and bases, but the same would hold true whether you're dealing with a weak acid strong base or a strong acid weak base. The similar reactions will take place, and they would have slightly different net ionic equations. I'll give you a few examples of other than strong acid strong base net ionic equations, so you can see what a weak acid strong base net ionic equation is and a strong acid weak base net ionic equation. But one thing you need to always remember about acid-base reactions is that it always produces a salt and water. Now the salt comes from the cation of the base and the anion of the acid. And remember, this is double displacement reaction. So in double displacement reaction, what does that mean? We take the two cations and we form two new products. So you take the two cations, switch them, we get NaCl and H2O. So you see we have a salt and water. So this would be the molecular equation. Again, you take the sodium and the hydrogen from HCl, and they switch positions. So again, this is the molecular equation. This is what the ionic equation would look like, and notice that since H2O is a liquid, it remains intact. It's not separated. And then notice that, let me go back so you can see that the cation and anion of the salt are the spectator ions, so they get crossed out. So the sodium and chloride are spectator ions, and what we have left is the net ionic equation. So again, for a strong acid, the reacting species is H+. For a strong base, the reacting species is OH-. So anytime you see HCl and NaOH, this is the net ionic equation. Now, if we look at another strong acid, strong base comparison, here we have nitric acid and potassium hydroxide. So again, we switch the hydrogen and the potassium to form two new compounds. Next, we write the ionic equation. Again, notice that H2O remains intact. The cation and anion that make up the salt are the spectator ions, and what we have left is the net ionic equation. So you notice that for both of these, we have the same net ionic equation. That's not a coincidence. That's always going to be the case when you have a strong acid reacting with a strong base. So again, anytime you have a strong acid reacting with a strong base, this is always going to be the net ionic equation. Always. So what's shown here is, again, a strong acid, strong base reaction. But let's say we have a weak acid. And so here we're going to do a weak acid and strong base. So for example, we want to react. So a weak acid would be something like hydrofluoric acid plus a strong base, say sodium hydroxide. And we're going to do the same thing. So the two cations switch position, we get sodium fluoride and H2O. So we get the same thing as salt and water. But now when we write the ionic equation, notice that HF is aqueous, sodium hydroxide is aqueous, NaF is aqueous. But since this is a weak acid, and this is very important to remember about weak acids, since this is a weak acid, this HF remains intact. So for weak acids, we don't break this apart. Again, for weak acids, on this side of the equation, the weak acid remains intact. Because it's a weak acid, we did not break this apart. This is one of the special, I guess, rules for weak acids when you're writing a weak acid strong base equation. So this would be HF aqueous plus so this would be the ionic equation, and what you see here is that the sodium is the only spectator ion. And so what we have left is the net ionic equation for a weak acid and a strong base. Yeah, I'm just showing you this so you can see what it looks like, but we're mainly interested in knowing the strong acid and strong base. So you can see the difference between a weak acid and strong base net ionic equation and a strong acid, strong base net ionic equation. So for a weak acid, the reacting species is the molecule of acid HF. So this is a weak acid and strong base. If I was to show you a strong acid and weak base, let's say we want to do one with a strong acid and weak base. Let's say we react HCl plus NH3 gives us H4 plus Cl minus. So in this case, this is a strong acid and weak base. We still get a salt, but since it's a salt because we have a cation and anion, just like we did with the others, but it's separated. Now for the ionic equation, again with weak base, just like with weak acid, we don't break apart the weak base. It stays as NH3. So we get this is our ionic equation. And notice here that these spectator ions are just the chloride ions. And so what we have left is the net ionic equation of a strong acid and a weak base. So anytime you have a weak acid or a weak base, when you're writing the ionic equation, net ionic equation, you don't break those two apart. So I just wanted to show you the difference between the different combinations of acid and bases.